Hello and welcome back. In the previous video, we discussed how adding or removing heat from an object can change the object's temperature. In this video, I want to study the different ways that heat can actually move from one object to another. So it turns out that there are three basic ways that heat can be transferred. There's convection, conduction, and radiation. So convection occurs when the actual fluid or object that is holding the heat physically moves from one place to another. So, for example, this occurs when you open up the door to an oven. So when you feel the heat coming from an oven, what you actually feel is the hot air leaving the oven and hitting you. This can occur either naturally or using fans. So it doesn't matter whether the convection is forced or it occurs naturally. Anytime there's a bulk movement of a fluid, and that's what's causing heat to transfer from one place to another, it's called convection. Another form of heat transfer is called conduction, and this occurs when two objects are physically in contact with each other. So what happens is when you have two objects that are physically in contact with each other, the atoms that are near the surface of those two objects will bump into each other, and as a result they transfer energy from one object to the other. Objects that transfer heat very effectively are called thermal conductors, and objects that transfer heat very poorly are called thermal insulators. Now, one thing that you might have noticed is that thermal conductors tend to be very good electrical conductors. So things like metal, for example, they tend to conduct heat and electricity very well. And it turns out there's a very good reason for this. Let me go ahead and open up a blank screen here. So one way that we can think about metals or any type of thermal or any type of electrical conductor. So a metal, if you think about this, basically what's going on inside there is you have a whole bunch of electrons that are basically just running around, right? So inside a metal, the atoms do not hold on to the electrons very well. That's why they're good electrical conductors. So one way to think about a metal block is it's like a box that's holding a gas of electrons. And the electrons are just bouncing around. So if you have two pieces of metal that are in contact with each other, the electrons can actually move from one box to the other. So what happens is when you have two pieces of metal that are in contact, you basically have convection occurring with electrons. So some of the heat that is transferred is basically like electron convection. You have some hot electrons from a hot object being transferred to the cooler objects, and some of those cooler electrons are transferred to the hotter object. And so this is one of the reasons why good electrical conductors tend to also be good thermal conductors. So let's go ahead and think about the different types of things that affect the rate that heat is transferred through an object. So we've already said that the rate that heat is transferred through an object is going to depend on the type of material the object is made out of. So for example, if it's made out of a metal, heat will be transferred through the object very quickly. If it's made out of an insulator, like a plastic, we expect that the rate that heat is transferred through it will be very slow. The rate is also going to depend on the difference in the temperatures between the two sides. So for example, if you have a very large temperature difference between two sides, heat will be transferred very quickly. However, if both sides of an object are very similar in temperature, then heat will be transferred very slowly. The rate that heat is transferred is also going to depend on the area of the object. So for example, if you have a really giant window in a room, you expect that that's going to be sort of bad for the efficiency of the house, right? That hot air outside will be able to move through that much more quickly than it would if you had a small window. Also, the rate that heat transfers through an object is going to depend on the thickness of the object. Again, hopefully that should make sense. So for example, if you lived in a house that had 10-foot thick walls all the way around it, it would be really well insulated from its environment. So the formula that describes the rate that heat is transferred through an object is given right here. So we can see basically everything we predicted. It's going to depend on the material, that's this constant K here. This is a property of a material called thermal conductivity, and it describes the ability for a material to conduct heat. The cross-sectional area is going to be proportional to the rate that the heat travels through it, and the difference in the temperature is proportional to the rate that heat travels through the object. And then finally, we can see that the thicker the object is, the slower heat is transferred through it. Now, the last form of heat transfer that I want to talk about is called radiation. And radiation is the heat that is transferred through light. Radiation is perhaps the single most important form of heat transfer because radiation is able to travel through the vacuum of space. So all of the heat that the Earth gets from the sun comes in the form of radiation. Now it turns out that every single object in the universe emits some light, and the rate that heat is emitted through this light is given by the Stefan-Boltzmann law, which I have written down here. This E here is something that is called the emissivity. And what the emissivity describes is it describes the ability for an object to absorb or emit light. The sigma in this formula is called the Stefan-Boltzmann constant, and it's a universal constant. A is the area, the surface area of the object. So objects that have a very large surface area can emit a whole lot of light. And finally, the T in here is the temperature of the object. Now, one thing I mentioned is I said that every single object in the universe emits some form of light. Now, that may sound a little bit strange because most of the objects that we see don't appear to be emitting any light. And there's a very good reason for this. Let me go ahead and open up a blank screen here. It turns out that the wavelength of the light, and the wavelength describes the color of the light, so it turns out the wavelength of the light that's emitted from an object is given by some constant that is called the Wien's displacement constant divided by the temperature of the object. Actually, this describes the most intense light that's emitted from an object. So objects actually emit light at a whole bunch of different wavelengths, but the most intense light will be at this wavelength. So for the sun, the wavelength that is emitted by the sun is approximately going to be equal to 660 nanometers. Now, for an object that is on the Earth, that is at just like, 25 degrees Celsius or so, the wavelength of the light that's emitted by this is approximately going to be equal to 9,500 nanometers. Now, the reason the wavelength is important is because, as I mentioned before, the wavelength of light is what determines the color of light. And our eyes are able to see wavelengths that range basically from about 400 nanometers at the low end all the way up to about 800 nanometers at the high end. So while the sun is emitting light that's right in the visible range, which is why we're able to see the light that's emitted from the sun so well, the light that's emitted by the Earth and objects on the Earth is way, way beyond the range that we're able to see. But this also is another important thing. This also allows us to explain the greenhouse effect. So let me go ahead and open up another blank screen. So if we think about what's actually happening, so you have the sun out here, and then we have the Earth. So the sun is emitting light in the form of radiation, or it's emitting heat in the form of radiation, and the Earth absorbs this heat. So if the Earth was absorbing the heat from the sun, and it just kept absorbing heat from the sun and absorbing heat from the sun, the Earth would heat up, and eventually it would just be this molten ball of lava. However, of course, that doesn't happen, because as I mentioned before, the Earth actually emits radiation of its own. But the color of the light that is emitted by the Earth is vastly different than the color of the light that's emitted by the sun, right? The wavelength that's emitted by the sun, again, is about 660 nanometers, whereas the wavelength of the light that's emitted by the Earth is approximately equal to 9,500 nanometers. So just like you can have stained glass that allows light of one color to pass through it while blocking other types of colors, there are gases in the atmosphere that will allow light that is emitted from the sun to pass through to the Earth, but reflect the light that is emitted from the Earth back towards the Earth. And the reason this can happen is because the wavelengths of these lights are so vastly different. So at this point, I think I'd like to end the discussion of heat transfer. And in the next video, I'm going to begin discussing the ideal gas law.